Hello again. In this lesson, we're going to learn about the simplest technique to segment an image, which is thresholding.
Image segmentation is broad and is evolving quickly, and deep neural network-based approaches are offering extraordinary accuracy. However, they come with considerable computational cost and significant training time. There are many simpler image segmentation problems where we should consider classical techniques instead. In this module, we'll divide classical image segmentation algorithms into 5 classes: thresholding, clustering, region growing, edge detection, and template matching. Each of these classes contain algorithms that have proven successful in particular domains, but none of them are applicable across all domains. Let's explore these techniques and see what they have to offer for real-world problems. In this section, we're going to have a look at the first and simplest image segmentation technique. There is also a related lab where we will take what we learn here and apply it to our first image segmentation problem. Thresholding is the simplest technique, and it's still pretty powerful, and for those reasons remains very popular. We can use it for very simple images. Normally we convert from grayscale to black and white, as black and white is simpler to work with. Okay, let's get started with some basic thresholding. This is going to be our Hello World image segmentation example. In the lab, we're going to take the image on the left, a starfish, and we're going to do our first project where we segment that image into starfish and not starfish using thresholding. So when we finish, each pixel will be assigned a label. In this example, blue is 1, and equals starfish, and black will be 0, not a starfish. The simplest approach is often the best, and we will work through a very simple approach where there is one threshold for the entire image. The simplest thresholding method can be thought of as supervised or experimental. Just replace each pixel in an image with a black pixel if the image intensity is less than some threshold, or a white pixel if the image intensity is greater than that threshold. Keep adjusting the threshold and repeating the replacement step until you've achieved a satisfactory result. Otsu's method can automate the process of finding an effective threshold and is popular due to its relative simplicity. Adaptive local thresholding is a more complex approach and uses techniques to divide the image into smaller segments and sets a different threshold for each segment. Color images can also be thresholded, and there's a number of approaches possible. For example, you can separate out the red, green, and blue channels and individually threshold each channel and then combine the results. And there are many other possible approaches. For our labs, we're concentrating on manual thresholding and Otsu's method. Okay, manual thresholding is about the simplest technique imaginable, and thus very powerful. It's capable of separating objects in very simple images. In this technique, we experiment with dividing our grayscale image into black pixels and white pixels by arbitrarily choosing a grayscale value, such that the grey pixels above our arbitrary threshold are converted to black, and pixels below our threshold are converted to white. Then we adjust the threshold experimentally and repeat until we are satisfied with the result. Let's see how we can use a histogram of an image to segment that image into foreground and background. Give us some hints where to apply the threshold. Here we have an idealized histogram of a theoretical image that we want to segment. Put another way, here's a bar chart. For each pixel in grayscale, let's say that pixel can contain an intensity value between 0 and 255, okay? So we count how many pixels contain a 0, how many contain a 1, etc., all the way to 255. And then we plot that. So in our diagram, our x-axis represents the pixel intensities from 0 to 255, and our y-axis represents how many pixels in our image contain that particular value. In the idealized histogram we're looking at here, please take heed of a few items. We can state that there's a clear group around 90 on the x-axis, and another clear group around 150, 160 on the x-axis. There seems to be a little dip around 127. So we're imagining that for this image, that the background pixels are grouped together around the peak at 150, and the foreground pixels are grouped together around 90. And we're saying that the best place to separate the background from the object is to use the grayscale value of 127. Let's call this our threshold. Put another way, we've used the histogram to deduce a reasonable threshold, and we're saying that any pixel below that threshold intensity goes to 1, becomes region of interest or object, and everything else goes to 0, becomes background. So we can see the original image on the left, and after manually choosing a threshold t and applying the thresholding function, we are left with a black and white image on the right. If we examine the image on the right, we'll see that we still have a degree of work to do to more cleanly separate the background colour from the object, and in the lab we'll work through some dilation, erosion and so on, until we're happy with the separation that we achieve. Otsu's method, named after Nobuyuki Otso, can be used to reduce a grey level image to a binary image. It has an interesting property for us. Effectively, the algorithm removes the supervision that we needed for manual thresholding. In effect, it finds a reasonable threshold algorithmically. If you recall, in the previous example, we converted the image to a histogram, plotted it, looked for a good place to separate the foreground from the background, and tried a few thresholds before finding a value we were satisfied with. Otsu's method exhaustively iterates through all possible threshold values and calculates the variance for the pixel levels on either side of the threshold, i.e. the pixels that fall either into the foreground or the background at that threshold. And the goal is to find the threshold value where the sum of the background and foreground variances is at its minimum. And that, for simple images, is usually a reasonable threshold. Unfortunately, as you can see, very quickly you run into classes of images where the threshold is not very clear. You can see the starfish on the left and its histogram on the right. This real-world histogram does not exhibit the clear foreground and background peaks separated by a clear dip that the idealist histogram we saw earlier exhibited. While it's certainly possible to segment this image, in fact we've a lab that does just that, it's worth noting that we're stretching the capabilities of simple thresholding already. And these images are not that complicated. So thresholding works best if you're splitting an image into 2 segments. If you're trying to split into more than 2 segments, you're probably better off trying a different method. They work best if there's a clear gap between the background and foreground, so you may need to think about controlling the environment from where you're selecting your images. Thresholding does not perform very well with noisy images, and Otsu's method exhibits relatively good performance if the histogram can be assumed to have bimodal distribution and can be assumed to possess a deep and sharp gap between 2 regions. If the foreground is small or large compared to the background, that histogram is no longer bimodal and Otsu is no longer effective. Now, let's briefly mention adaptive thresholding. This is another extension to basic thresholding, where the image being thresholded is not treated as one single homogeneous image for the purposes of thresholding. Instead, the image is split up, and different values of t are calculated for different parts of the images. And examples include OpenCV's mean C and OpenCV's Gaussian C, where the threshold is calculated as a mean of the neighbourhood area or as a weighted sum of the neighbourhood values, where the weights are a Gaussian window. Okay, that's our first family covered. Despite their limitations, they are quite useful due to their simplicity.
In this lesson, you practice segmenting your very first image using the thresholding technique. Congratulations! At this stage, you should have a feel for the type of issues real-world images present to us, and be starting to understand what you can do to deal with them. This is a really useful technique, and you can already segment simple images using it.